the near future, a slowly moving vehicle will travel from the towering vehicle assembly building to Launch Complex 39. Its burden, the 360-foot-high, million-pound Saturn V. From the launch pad, the 7,500,000 pounds of thrust from its first stage will hurl the Apollo spacecraft and its three-man crew on the beginning of a trajectory that will take them to the moon. When the lunar mission is launched, the space vehicle will initially enter a parking orbit around the Earth. After the required checks have been performed, the space vehicle will be injected from the parking orbit into its translunar trajectory. A free return trajectory is planned. That is, if anything should go wrong with the primary propulsion system, the space vehicle would loop around the moon, return to Earth, and land safely. However, assuming that everything operates as it should, the space vehicle will approach the moon, then go into orbit around it. A lunar module will then be detached from the main space vehicle, and its crew will land it on the lunar surface. After a period of lunar exploration by the astronauts, the lunar module will lift off, rendezvous, and dock with the orbiting spacecraft. Then the entire crew will return to Earth, leaving the lunar module in orbit around the moon. However, because of natural and operational constraints, you can't launch a lunar mission whenever you want to. The determination of when the mission can be launched is a highly complex task. The time periods during which you can launch and accomplish the goals of the lunar mission within the applicable constraints are called launch windows. There are two launch windows to be considered: a daily window measured in hours and minutes, and a monthly window measured in days. It is desirable to have the launch windows as large as possible for operational flexibility. To see how constraints limit launch windows, let's look at the days available for an entire year on which a lunar mission could be launched. If only a single landing site were available on the moon, all days but these would be eliminated. The determination of the time and duration of these launch windows is the subject of this film. We will first examine the daily window, the hours during a day when we can launch the lunar mission. The duration of the daily window is directly related to the range of allowable launch azimuths. A launch azimuth is simply the direction measured from due north along which you launch. A launch due north would be on an azimuth of 0 degrees. A launch due east would be on an azimuth of 90 degrees. The larger the window, the larger the required azimuth range. The limitation of the launch azimuth on the daily window is defined by range safety requirements and insertion tracking requirements. The range safety requirements are primarily concerned with keeping the launch vehicle within the bounds of the launch range. These bounds are designed to avoid populous land masses in case of trouble during the launch. These azimuth limits are approximately between 72 degrees and 108 degrees. There is an operational requirement to track the space vehicle during the complete launch phase and from orbit insertion to at least 3 minutes following insertion in order to verify that an acceptable orbit has been achieved. Some tracking coverage is obtained from stations on Bermuda and Antigua. However, since insertion can occur beyond these stations, the gap is filled by a tracking ship which can track over a launch azimuth range of 26 degrees. The choice of where this 26 degrees is located within the 72 degree and 108 degree limits is left to the mission planner. Reviewing then, the duration of the daily window is directly dependent on the range of launch azimuths or directions in which you can launch, as restricted by range safety and insertion tracking requirements. Before proceeding, it is necessary to take a look at the Earth-Moon geometry. The Earth-Moon geometry combined with the launch azimuth constraints is what defines the duration of the daily launch window and the time during the day when it will occur. If a line is drawn from the center of the moon through the center of the Earth, penetrating the surface of the Earth on the opposite side, the point of penetration is called the antipode, which means point opposite. Injection onto the translunar trajectory should come at or near the antipode for maximum efficiency. The antipode will be calculated not from where the moon is at launch or injection, but from where it will be at time of spacecraft arrival. The space vehicle will be placed in a parking orbit around the Earth so that required systems checks may be accomplished. The injection burn, or firing of the rocket engines to place the space vehicle on its translunar trajectory, will be accomplished on one of the first 3 orbits. The injection would place the spacecraft in an elliptical orbit with perigee at the antipode and apogee near the moon, provided the orbit were not affected by lunar gravity. However, the lunar gravity will perturb the orbit, so it is necessary to lead the moon by a few degrees. This means the injection burn must actually occur a few degrees after passing the antipode. Summarizing then, the antipode, or point opposite, will be calculated from the moon's position at time of spacecraft arrival, not at time of launch or injection. The translunar injection burn will occur in Earth parking orbit. The engines will be ignited so that the effective point of injection will occur a few degrees after passing the moon's antipode on the surface of the Earth to lead the moon and compensate for lunar gravity. We have seen that in order to get to the moon, we must first get to the antipode. We must now look at the problem of getting to the antipode from the launch site at Cape Kennedy. To do this, we must know the antipode's position and movement relative to the launch site. The antipode position on the Earth's surface will define the time when a launch must occur for a given launch azimuth. We will show why. We will also show how this is combined with the launch azimuth constraints to define the duration of the daily launch window. The movement of the antipode is caused by 2 separate motions. 1, the monthly revolution of the moon around the Earth, and 2, the daily rotation of the Earth on its axis. It's convenient to examine these motions separately at first. If the moon revolves around the Earth, and the Earth with the launch site is assumed stationary, the antipode will trace a great circle on the surface. This accounts for an antipode movement of about 0.54 degrees per hour in a west to east direction. The monthly antipode trace would look like this on a flat map of the Earth. If the moon is assumed stationary and the Earth with the launch site is rotated, the antipode will trace a path moving at 15 degrees per hour in an east to west direction. This will not be a great circle and will look like this on a flat map of the Earth. The monthly trace and the daily trace are combined to determine the position of the antipode relative to the launch site. The launch must occur at a certain time for each launch azimuth in order to intercept the antipode. This time is defined by the antipode's position, the time interval from launch to arrival at the antipode, and antipode travel during this interval. The launch must be timed so that the vehicle intercepts the moving antipode. The launch window duration is defined by the time it takes the antipode to travel from interception of the 72-degree launch azimuth to the 108-degree launch azimuth. It can also be seen that the antipode trace will twice intersect the orbit plane that results from any given launch azimuth. Thus, there are 2 correct times at which to launch. If at the first correct time the spacecraft is launched on a given launch azimuth, it will intercept the antipode over the Pacific Ocean. At the second correct time, later in the day, a launch on the same azimuth will provide an interception of the antipode over the Atlantic Ocean. Thus, there are 2 launch windows available on any given day. When the spacecraft intercepts the antipode over the Pacific, it is moving in a northeasterly direction. Over the Atlantic, the spacecraft is moving to the southeast. The direction of travel is important, as will be shown later. Reviewing then, we see that in order to pass over the antipode for translunar injection, we must first determine where the antipode is relative to the launch site. We do this by combining the monthly movement, determined by the moon's travel around the Earth, with the daily movement, determined by the Earth's rotation. Knowing the ground track that results from a given launch azimuth, the correct launch time for each azimuth can be determined. We have also shown how the movement of the antipode results in 2 interceptions with the ground track for each launch azimuth. Once over the Pacific, with the spacecraft moving to the northeast, the other over the Atlantic, with the spacecraft moving southeast. We must now consider the monthly launch window. A monthly launch window allows the mission to be rescheduled as soon as possible in case it is scrubbed for a given day, or a hold extends beyond the daily window. This also allows some flexibility in initial planning of the launch day. A major factor in determining the minimum acceptable duration of the monthly window is the turnaround time of the space vehicle. From operational considerations, it is desired to have a launch window of several days. In order to understand other monthly launch window constraints, it is necessary to look at other phases of the lunar mission. The effect of constraints is to eliminate launch opportunities. As the constraints are applied one by one, possible launch dates are eliminated. The possible launch dates left after all constraints are applied represent the monthly launch window. The primary factors that limit the monthly launch windows are the lighting conditions on the moon at the time of lunar landing, the performance requirements to get the spacecraft to the particular lunar landing site, and the location of suitable landing sites on the moon. We will first examine the effect of performance limitations, then take up the lighting requirements at the time of lunar landing, and then the location of the lunar landing site. By performance, we mean the capability of the spacecraft to maneuver in space and make necessary changes in its orbit during the Earth and lunar orbit phases of the mission. This is directly limited by the amount of propellant it can carry. Before we can go further, it is again necessary to look at the Earth-Moon geometry. As the moon revolves around the Earth, with the Earth as its center of revolution, the plane described by the lunar orbit is called the moon orbit plane. The moon orbit plane is inclined to the Earth's equatorial plane at an angle of about 28 degrees. As the moon moves around the Earth, it changes its position relative to the equator. The angle between the equatorial plane and the Earth-Moon line is called the angle of declination. This angle varies from about 28 degrees when the moon is here to 0 degrees when the moon is here. Since the spacecraft is traveling to the northeast when translunar injection occurs over the Pacific, a Pacific injection will place the spacecraft north of or above the moon orbit plane. An Atlantic injection with the spacecraft moving southeast will put the spacecraft south of or below the moon orbit plane. The angles of inclination of the translunar trajectory with the moon orbit plane have direct bearing on the landing areas attainable on the moon. Following a Pacific injection, the spacecraft approaches the moon from above the moon orbit plane. This forces the trajectory below the plane on the far side of the moon where lunar orbit injection takes place, and back up to the northern latitudes on the front side where the landing areas are located. This makes Pacific injections more favorable from a performance standpoint for landing sites located at northern latitudes, since less plane change is required to reach these sites. An Atlantic injection would, of course, be more favorable for landings in the southern latitudes. The performance limitations of the spacecraft determine the latitudinal boundaries of the accessible landing area for any given day. The spacecraft, as it enters lunar orbit, must make a plane change so that its orbit plane contains the landing site. The amount of plane change it can make, directly related to the amount of propellant it can carry, is what limits the range of latitudes. This area, as determined by a combination of spacecraft performance and geometric constraints, is centered around the trace of the moon orbit plane. Because of the ascending and descending movements of the moon, the lunar latitude bounds will vary. This variation is cyclic, with a period equal to that of the Moon's orbit around the Earth. The accessible area must be determined for each possible lunar arrival date in order to determine whether a proposed landing site is available on that date. The possible landing sites must lie within the accessible area at the time the spacecraft arrives at the Moon. The final major constraint on monthly launch windows is the sunlight requirement at the time of landing on the Moon. This, combined with the number and locations of suitable landing sites, represents the last major limitation to the monthly launch window. These factors are inseparable in their effects on launch windows. In order to provide the landing crew with best possible visibility during landing, the sun elevation angle must be between 7 and 20 degrees, or within a 13-degree range. Since the Moon rotates at about 13 degrees per day, this means that any particular landing longitude is open only 1 day per lunar month, if the lighting constraint is not to be violated. It can therefore be seen that any specific landing site is available only 1 day per month. Since a free return trajectory has been chosen for safety reasons, and transit time on this type of trajectory has only a very small variation, the time of travel from Earth launch to lunar landing is relatively fixed. This means that only 1 day per lunar month is suitable for launching the mission. That is, if you must land on this day, since it takes approximately 3 days to get there, you must launch on this day. In order to provide multiple launch opportunities, multiple landing sites must be available, 1 additional landing site for each additional launch opportunity. The total interaction of factors affecting the launch window can be summarized as: given a lunar landing site, a launch is possible only on the day that the lighting is acceptable, and then only if the landing site is within the latitude bounds attainable for that longitude on that day. We have seen how the daily launch window is developed and the development of the monthly launch window. Now let's look again at the launch windows possible throughout a year. The entire set of constraints may be placed into 2 areas: the performance of the overall space vehicle system and the lighting of the landing site at the time of landing. Let us assume, as we did at the beginning, that only 1 lunar landing site has been selected. Space vehicle performance constraints would eliminate all days but these. Adding on the lighting constraints would eliminate all days but these, which leaves only these days out of an entire year when it would be possible to launch the lunar mission. However, if we assume more landing sites, for example 7, the number of days you can launch is expanded to these. Determination of the lunar launch window is just one part of the mission design. Trajectories for all segments of the lunar landing mission, including translunar, lunar landing and rendezvous, trans-Earth and Earth entry, will have been computed for nominal and contingency cases before man can begin his historic rendezvous with the Moon.